Hey everybody, it's me, your old pal Dingo the Clown. Today, welcome to the Mr. Lowe's Physics Show class thing. So today we'll be covering a review of electrical stuff that happened in class before all this crazy business. So stay tuned. How do I turn this off? Sorry. Stop. I got it from here. Sorry about that. It's hard to find good help in these trying times. Hi, I'm Mr. Lowe. I'm your physics teacher. Welcome to physics class online. So here's what we've got. I have a camera, so you can see me. I have a dot cam, so I can write stuff on here for you. We can do notes or whatever, and I don't have to wait for you to write. You can just pause it, and I think that's great. So stay tuned, and we'll get right into it. Still learning how to pause. Okay, so let's review from about where we left off. I'll kind of start the whole thing over. What is the smallest thing you can think of? You're wrong. Think smaller. Nope, smaller. Smaller.
A peanut.
No, not a peanut.
Half a peanut.
Okay, smaller than that.
Ant-Man.
Yeah, I guess Ant-Man's pretty small. But what I'm thinking of is one of the most fundamental particles of the universe, and that would be the electron, okay? This is not an actual electron, although it does contain electrons. This is a plastic ball, okay? But for our purposes, it's going to be an electron, okay? Electron is very, 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 very tiny. It's the smallest thing there is, really. Okay, so there's that. We have electrons. Electrons, are negatively charged, right? You see that minus sign? That means it's negatively charged. What does charge mean? We'll try to develop a sense for that in the coming future. Okay. What else do we have in terms of tiny particles? Well, I've got, okay, this is my electron, right? Over here, I have a proton. Look at that. Look at this. Look at these guys. The proton is much bigger than the electron, much more massive, okay? It's very heavy, relatively speaking. It's very tiny, but you get the idea. So it's actually kind of more like this, right? The electron is about as tiny as you could imagine, especially compared to the proton size-wise. But look at this. Their charges are equal, but opposite. Okay, same charge, just the electron is negative and the proton is positive, okay? One third thing we should discuss is the neutron, right? The neutron is like the proton, right? Exactly the same mass, except it is neutral. There's no charge. It's not positive, it's not negative, it's just neutral. Hey, there's no charge for neutrons today, right? Neutrons are free of charge! Still learning how to pause. Sorry, not proud of that. Anyway, we have the neutrons and the protons, right? So, neutron, proton, positively charged, same mass. Same charge, where is it? Proton and electron, different mass. But same charge, right? But opposite. Okay. Another thing we need to look at is if I have two charged particles that are similar, right? Like these two electrons here, they are going to attract or repel. Right, they repel. Very good. Similarly, if I have two positively charged particles, they could be protons, they don't have to be because it doesn't matter. Also, the positively charged particles are going to repel, right? It's just the way it is. If I have a positive and a negative, they are going to attract. That's about it for that. Here's, that way. Here's some notes I made. You might want to start putting this in your notebook. Here's a model of the atom. This is supposed to be circular, and I apologize for that. But we have the nucleus, and I can even write that here, which consists of protons and neutrons. The nucleus in the center, and that is orbited by electrons. Okay? And what an atom is going to tend to do is seek neutrality. So if there are two protons in the nucleus, it's going to be happy when there are two electrons orbiting it. Then the thing is overall neutral. It has an overall neutral charge. Okay. Okay, while you have your notebooks open, why don't you throw something like this in there where you are able to, this is what I want from you out of today, basically. So you're able to explain the mass and the charge of the proton, right? These two, I could even say, oops, my bad, are equal mass. It's supposed to be mass. You get the idea, right? Proton and neutron are heavy, but mostly, the electrons are light, okay? Mostly what we're interested in this unit is the charge of these guys. So a proton is positive, neutron is neutral, and electron is negative. You're going to want something like that in your notes. Also, we have some key ideas that I will just touch on briefly. Let's do this. There are two kinds of charge, positive and negative, right? Opposite charges attract. That's these guys. Oops, no, I do that wrong every time. Okay, these guys, right? They will attract. You kiss. Similar charges repel. They want nothing to do with each other. Same here. These positives, there we go, will repel, right? Oops, that's here. Charge is conserved. Remember when we talked about energy, we said energy is a conserved quantity. You can't create it or destroy it. Same with charge. You cannot create or destroy charge. Whatever is in the universe is in the universe. We can move it around just like energy, right? I can move electrons around, and I want to get used to that idea. But we can't just create charge out of nowhere. Okay? Something that is made up of equal numbers of positive and negative charges is considered overall neutral, right? You've got gajillions of protons and neutrons in your body that make you up, but there's roughly an equal amount of them. So overall, you're considered electrically neutral, and that's why we don't go around shocking each other. But sometimes, if you rub on the carpet, you steal electrons from the carpet, and you can touch the doorknob or touch your little brother or whatever your way of getting that out of your system would be. But when you do that, you have more electrons than you do negative, so you have more negative charges. I'm sorry, you have more electrons than you do protons, and so you have more negative charges than you have positive charges, so you're able to zap your little brother. Which leads me to the next thing, and we never talked about this, but here you go. Objects can be charged by transferring electrons either by induction or conduction. Okay, and here is a little resource. I might upload this for you. Here's the difference between induction and conduction. Okay, induction is when I bring a balloon. Okay, here, let's do this. When I rub a balloon against my hair, pretend that I have hair, that's conduction. I'm conducting, I'm stealing the electrons from, the balloon is stealing electrons. I can't keep it straight. When I bring it over by your hair and it kind of stands on end like that, that is induction. It's a force at a distance, right? I'm attracting the electrons that are in your hair by the positively charged balloon, basically. Okay. And one last thing I want to talk about. This is all stuff you can put in your notes. I had it handy. So here you go. So let's look at this. Charges added to one part of an insulator remain on that part. Okay. And we didn't talk about this. There are two kinds of materials: insulators and conductors. Right? Conductors are metal, basically metals, where electrons are free to flow. Things you would imagine that electricity could flow through. So, like a bathtub is a great conductor. Your body is a pretty darn good conductor. That's why the electric chair works, not to get dark. But things that can conduct electricity are called conductors. Makes sense. Um, oh, and then we also have insulators, right? That's things where electricity or electrons are not able to flow as easily, right? Because the flow of electrons is what we think of as electricity. We'll get to that in a second. Um, so materials where electrons don't flow easily, like wood or porcelain or plastic, things like that, where you couldn't get a shock through. It's not going to conduct electricity. It's not going to. The electrons aren't able to flow through the material. Okay. So the difference here, I've got conductors and insulators. If I add electrons onto an insulator, like a styrofoam ball, if I touch it with a charged wand, right? Boom, and we can really charge up a wand. If I touch it with some charged object, the charges are going to stay right where I put them, right? My pen is positively charged, and I touch this styrofoam ball. It goes boink, boink, maybe a little tap there and another tap there. It's going to leave. Oh, I guess I stole electrons. Zoop, 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 zoop. Either way, I put a charge on the thing, it's going to stay right where I put it. Whereas a conductor, if I put a bunch of, these are positive, but let's say negative. If I put a bunch of negative charges on a ball of metal, and they flow pretty easily, right? They can flow through this material pretty easily. So we have two things. They're on a material where they can flow easily, and they're repelling each other, right? Because they're similar charges, so they repel each other. If they can repel and they're free to move around, they're all just going to get as far away from each other as possible, right? Which is not bad advice for you guys, too, in this coronavirus epidemic, right? You want to stay as far away from each other as possible. In this material, they're able to do that. In this material, they're not. They have to kind of stay stuck in the mud there where you put them. Okay, that's enough of that. Electrons are negatively charged particles. Protons are, my bad, positively charged particles. And this is very important. Electrons are free to move. Protons are not. Okay? And the protons are going to stay put. We could retitle this section pushing electrons around, because that's really what this is all about. We're just moving electrons around. The protons stay put. Okay. And then I've got some. These are like problems that you would be expected to be able to answer. I've got just qualitative things about key concepts, how many different charges are there, positive and negative, stuff like that. And then, you know what, hold off on that. I'll let you know if we're doing things with charge. Okay, I should have just stopped this about 2 minutes ago. Well, I think that's all I wanted to cover really in the review, and it was kind of a practice just to see if we could get this stuff to work. I'm gonna get to work now on a video for this week, which is resistors and circuits and stuff, and I want to get you guys set on circuits because I know we didn't talk about it. Okay. Was there anything else you wanted to cover, Dingo?
No, I think I'm good.
Okay. Well, then why don't you say goodbye to everybody?
So long, everybody.
Okay, and so long from me too. I'll see you. Hopefully, I'm gonna get started on the next video soon, and hope you're all doing well. I miss you. Okay, bye.